We have seen before how electron donating groups by resonance can donate electrons to the benzene ring, therefore in general increasing the nucleophilicity of that substituted benzene in electrophilic aromatic substitution reactions. Let's now see how the hydroxyl group in phenol can behave as an electron donating group by resonance. So let's draw the structure of phenol or hydroxy benzene, and of course oxygen in phenol has 2 lone pairs, therefore it can donate electrons by resonance. So let's do that. So we can take one of these lone pairs to make a double bond between oxygen and this carbon, and as a result this carbon-carbon double bond is broken, and of course the electrons are then released on that carbon. Now this will give us another resonance form where there is a lone pair on this carbon as a result of this electron donation by resonance by the oxygen atom. Remember, oxygen now has a positive charge. That's because the formal charge is actually +1. We can continue to delocalize electrons on this benzene ring by taking that lone pair and making a double bond here, and consequently breaking this carbon-carbon double bond. This will give us another resonance form where it has a lone pair or 2 electrons on that carbon. We can continue in the same manner by delocalizing electrons on the benzene ring by taking this lone pair and now making a double bond between that carbon and that carbon, and as a result breaking that carbon-carbon double bond. Now this will give us an additional resonance form that has a lone pair on that carbon. So we can clearly see as a result of this resonance donation that the oxygen atom in the hydroxyl group, because it has a lone pair, it can donate electrons by resonance. Therefore the electron density on the benzene ring is now increased as a result, and the nucleophilicity is also increased, and therefore the reactivity of hydroxy benzene or phenol in electrophilic aromatic substitution reactions is actually more or higher than unsubstituted benzene itself. Now we have to mention that in hydroxy benzene or in phenol, let's draw the structure again. This is phenol. Oxygen that's bonded to carbon is more electronegative than carbon in this oxygen-carbon bond. So therefore, oxygen pulls electrons or withdraws electrons toward itself in this covalent bond. So if this happens, now this leaves a positive delta on this carbon and a negative delta, or a positive partial charge on this carbon and a negative partial charge on oxygen as a result of this inductive effect. So it's actually inductive withdrawal. So this is inductive withdrawal, and obviously what we have done before is resonance donation. Yeah. Now this inductive withdrawal would as a result or inductively withdraw electrons from the benzene ring, reducing its electron density. So therefore, if the electron density is reduced, its nucleophilicity is subsequently reduced, and therefore the reactivity is lowered. So there are two opposing effects here. Resonance donation, which can or which does increase the nucleophilicity in this substituted benzene, and inductive withdrawal, which reduces the nucleophilicity of this substituted benzene. So there are two opposing electronic effects, but the hydroxyl group is an electron donating group by resonance because its resonance is actually strong. Its resonance donation is stronger than inductive withdrawal. In other words, the resonance donation of the hydroxyl group outweighs the inductive withdrawal or the withdrawal of electrons by inductive effect. So this resonance donation is stronger than inductive effect, and that's exactly why the hydroxyl group is generally described as an electron donating group by resonance.